Hello everyone, this is Yali and welcome to this video. Today I'm going to talk about one of my papers, Perimeter Control with Real-Time Location Varying Cordon. This paper is published in the top-tier journal, Transportation Research Part B, Methodological. Well, this paper is in collaboration with Dr. Reza at Data61, as well as my advisors, Mohsen Ramezani, without whom this would really not have been possible. So, about this video, I would like to give a general introduction of the paper. And for more details, you are more than welcome to read the paper. Every day, many people start their trips, and lots of people face traffic congestions during morning commute. Every people hates traffic congestion, and it keeps getting worse. Therefore, it's particularly important to design and implement effective traffic control methods. For a large urban network, one notable control method is perimeter flow control based on microscopic fundamental diagram. We call MFD for short. And it gives a well-defined relationship between network vehicle density and outflow for a region. It should be mentioned that heterogeneous networks may not have well-defined MFD, since the hysteresis phenomenon has been observed in the decreasing part of the MFD. So, a general approach is to partition the network into several homogeneous regions with small variance of link densities. These regions can be squares, hexagons, or any other shapes, such that the MFD can be utilized to introduce elegant control approaches to improve the network mobility. In this paper, we consider that an urban network is divided into two regions with 19 subregions. The network structure is shown in the left figure. The peripheral area is region 1 and the centered area is region 2. There are several hexagons. Each hexagon represents a subregion. We developed two models in the paper. The region-based model as the model used to design the controller, and the subregion-based model is to represent the real network. The perimeter control is designed based on linear quadratic regulator theory to obtain the control values. And also we proposed the real-time location varying cordon to change the locations of the perimeter controller. Behind the location varying cordon, we proposed the cordon selection algorithm. The algorithm associates an index to each subregion, quantifying the extent that the subregions need to be protected from hypercongestion, such that the algorithm clusters all the subregions either to the centered region or the peripheral region, that always keep two regions in total. Okay, let's take a look at the video. You can see that the number of vehicles in each region is changing over time, with higher number of vehicles in centered region and lower number of vehicles in the peripheral regions. The controller located at region boundaries always not switch locations in no control and static cordon case, while in the third case, the locations of region cordon varying. It can be seen that the changing cordon case, the controller can track the congestion propagation and limit the number of vehicles going inside the subregions with higher accumulations. Okay, let's take a look at the results of this paper. The top three figures show the accumulation evolution of no control, perimeter control with static cordon, and perimeter control with location varying cordon. As you can see from the figures, the network is not cleared in no control case, since there are several vehicles left at the end of simulation. Also, many subregions become very congested as the accumulation in those subregions are very large. In static cordon case, subregion 19 becomes very congested since this subregion is not directly controllable in this case. While in location varying cordon case, vehicles are uniformly distributed in the network, and the network gets emptied at the end of simulation. For the vehicle's total time spent in the network, the location varying cordon improves the network performance by reducing the total time spent around 57%. We can say it's a big improvement in eliminating traffic congestions. Okay, that's all for today's video. Bye.